This is part 7 of the series Parallel and Perpendicular Lines, and in the last part we began going through the proofs of the perpendicular lines theorems, and we're going to continue on with that idea with the proof of the perpendicular transversal theorem. So here we have two lines that are parallel, and one of those lines is perpendicular to a transversal. We need to prove that the other line, line N, is perpendicular to line L. So I've written down my given, and in usual fashion, we're going to go ahead and see if we can come up with a plan for this proof. Now, I can see that these two lines are parallel, and they already have one angle that's congruent. Now, what I'd like to do is I'd like to see if I can use the fact that these two lines are parallel to show that these two angles have to be the same. Well, the first thing I'm going to do here is I'm going to go ahead and I'm going to write in some angles because I need to have that information for working these proofs. So I'm going to call this angle angle 1. So let's just write a 1 in here. We're going to call this angle angle 2. And that just will help us out a little bit in working through this proof. Now, the first thing I want to be able to do is I want to be able to show that angle 1 is congruent to angle 2. And I should be able to do that in one step, because if two parallel lines are cut by a transversal, then the corresponding angles must be congruent. That's the corresponding angles theorem, or actually corresponding angles postulate. It's also a theorem, but it doesn't really matter which one you use. So if I know that these are parallel, then this angle must be congruent to this. And therefore, since these two angles are congruent, this angle must also be a right angle because its measure is 90 degrees. And since this angle is 90 degrees, this must be perpendicular to that by the definition of perpendicular lines. So there's the overall thumbnail sketch for what we're going to prove. And the reason I chose that direction is just it jumped out from the picture here that because I have two parallel lines cut by a transversal, those corresponding angles have to be congruent. And I always like to start with those postulates if possible, because it usually makes for the easiest entry point. So that's what I'm going to do. So now we've said that angle 1 is congruent to angle 2 by the corresponding angles postulate. Now this is the point where it can get a little confusing for folks, because there are a great many little details that you need to take care of that it's really easy to skip by. And if you're confused, always err on the side of putting too much detail versus not enough detail, because you never can tell if it's going to be assumed that you're just kind of guessing versus you know the pattern and the path that you have to take and the logical progression. So if you can show that logical progression, then there's no doubt that you know what you're doing. But again, it's difficult in situations like this to determine how much detail is too much and how much is enough. I always err on the side of too much detail versus not enough. So the first thing we got to get to, remember we've got to get to line L is perpendicular to line N. So that this line is perpendicular to this. So somehow we have to show that this is a right angle. Well, we can't just do it from here, because there's no postular theorem that would tell us that because angle 1 is a right angle, angle 2 is a right angle. We have to kind of go a longer way around to show that. And for that matter, we haven't even yet said that angle 1 is a right angle. Remember, our given was simply that line L is perpendicular to line M. So that would be one piece of detail that we'd want to put in there. We'd want to add that line L being perpendicular to line M, that makes angle 1 a right angle. So that's the first thing I'm going to add. And so what it means for two lines to be perpendicular is the definition of perpendicular lines. If two lines are perpendicular, then they intersect to form a right angle. Therefore, angle 1 is a right angle. Now, it's questionable, it's debatable whether or not this was necessary, but again, I like to err on the side of too much detail versus not enough. So what does this tell us? Well, that tells me that the measure of angle 1 is 90 degrees. So that's the definition of a right angle. Well, I've set up here that angle 1 is congruent to angle 2, what does that mean? Well, that means that the measure of angle 1 is equal to the measure of angle 2 because of the definition of congruent angles. So that's what I'm going to say next, because remember, I've got to show that this one is a right angle like this one is. So that's what I'm going to do next, because that gets me one step closer. Well, this kind of got me almost to where I need to be, because you can see here that if the measure of angle 1 equals the measure of angle 2, and the measure of angle 1 is 90 degrees, I can substitute this angle 1 for 90 degrees. And then I will have the statement 90 degrees equals the measure of angle 2, which in essence tells us that angle 2 is a right angle, which in turn tells us that line N is perpendicular to line L, and that's where we needed to get to. So I'm going to go ahead and make that substitution here. Now, in actuality, you could have used the transitive property if you wished. You could say that because 90 is equal to angle 1, and angle 1 is equal to angle 2, then 90 equals angle 2. That's also the transitive property of equality. So it would be equally valid to have used transitive property of equality here or the substitution property of equality. It really doesn't matter. I used substitution just because it was the first thing that popped into my head when I looked at it. All right. Well, now that we know that the measure of angle 2 is 90 degrees, we know that angle 2 is a right angle by the definition of a right angle. And now we know that line L has to be perpendicular to line N because we just stated that angle 2 is a right angle. So by the definition of perpendicular lines, line L is perpendicular to line N. So two lines are perpendicular if and only if they intersect to form a right angle. And there's your proof. Now again, you could have simplified this and cut out some of these steps, but it's always better to err on the side of more detail than less. Okay, so now let's move on to the last of our perpendicular line theorem proofs, lines perpendicular to a transversal theorem. Here we have a picture with the lines perpendicular to a transversal theorem and a given statement that says line L is perpendicular to line N, so L is perpendicular to line N, and line L is perpendicular to line M. So this is perpendicular to this, and this is perpendicular to this. And they show that these are right angles. This could kind of be a little misleading from the standpoint that we know from the four right angles theorem that if two lines are perpendicular, all four of these angles are right angles. So it really doesn't matter which one is being shown as the right angle. I know that all four of these are right angles because of that theorem. So this would be kind of inconvenient to use, even though we know that if we can show that two consecutive interior angles are supplementary, then these lines are parallel. That's probably not going to be the easiest way to execute this proof. So I'm probably going to use corresponding angles because that's generally the way I like to think. I like to use the postulates whenever possible. So that's probably what I'm going to do. So just to start off with, let me go ahead and label these so that I don't get confused as we move ahead in the future. This is going to be angle 1. I'm going to call this one angle 2. And don't let this confuse you. This is a right angle. This is a right angle. All four of these are right angles. All four of these are right angles. So my general plan for the proof to show that line M is parallel to line N is to show that angle 1 is congruent to angle 2. And we use the fact that if two lines are cut by a transversal, so the corresponding angles are congruent, then the lines are parallel. And that is the corresponding angles converse postulate. So that's what I'm going to try and do here. My first step then is to show that these two angles are congruent. In order to do that, I'm going to show that these two angles are right angles. In order to do that, I make the statement that this angle is a right angle and this isn't a right angle because of the four right angles theorem, which says if two lines are perpendicular, then they intersect to form four right angles. So using the four right angles theorem, I know that these two are right angles because we're given that they're perpendicular, and if two lines are perpendicular, then they intersect to form four right angles. And now I know if this is a right angle and this is a right angle, then these two angles have to be congruent. That's the all right angles are congruent theorem. So I know that angle 1 is congruent to angle 2 because of the all right angles are congruent theorem. And so I'm almost where I need to be, since angle 1 is congruent to angle 2, and these are corresponding angles. Then I know that line M has to be parallel to line M by the corresponding angles converse postulate. And that's our proof. So this proof, it would have been a little bit more difficult had we gone with the way this picture was presented, that this angle and this angle are right angles, because you would have had a little bit extra work to show that these are supplementary angles. But this is probably the most straightforward and the quickest approach to the final. All right, now we're going to move on to another idea of parallelism and perpendicularity using coordinate planes. So that's what we're going to start next. The first thing we're going to deal with when dealing with parallelism and perpendicularity in coordinate planes is the idea of slope. So none of these ideas are new. You should have seen these in your algebra classes in the past, but we're going to do a recap here just to make sure that everybody's got this down. So the first concept is slope. Slope in this country is given by M. In other countries they use other letters, but we use M for slope here. And slope is rise over run, which is the change in y. This triangle here is the Greek letter delta, which means change in. So the change in y divided by the change in x. And the change in something is generally represented as a difference. So the difference of the y's divided by the difference of the x's. And an easy way to think of this, to associate rise over run and with the y's and the x's, is the rise is the difference in the y's. So rise and y's kind of rhymes, kind of silly, but it's a way to get you to associate, because the biggest mistake people make when calculating slope is they swap these two. They take the reciprocal, they put the x's over the top of the y's. So it's the difference of the y's divided by the difference of the x's. Now, what we're going to do before we get into any greater detail is we're going to actually calculate the slope of various lines to look at the slopes of lines in a coordinate plane. And here is a picture of how we do that. If we're given 2 points, the coordinate of this is x1, y1, coordinate of this, x2, y2. We know that this distance is y2 minus y1. That would be an example of the ruler postulate that we looked at way back at the very beginning. And the distance between these 2 points is x2 minus x1. So we're going to be calculating slope using this difference divided by this difference, the ratio of the difference of the y's divided by the difference of the x's. So that'll effectively wrap up this session. What we're going to do at the beginning of the next session is we're going to use this idea to actually calculate the slopes of lines in a coordinate plane and talk all about that. So I will talk to you in the next video.